Okay, so we can start now. So, uh, so right here, this is uh, the eighth time we are appearing for this tutorial session, and the final time we are going to discuss the problems for your advanced quantum mechanics course related to this week's topics and also the assignments, which is more or less based on. Today we will specifically talk about scattering theory and some related problems. So that would might help you to get along with your questions that has been asked in your assignment for this week. And I hope you are going well with this course. You have found the I mean uh, the right reason why you have been like uh, advancing with this course, because this is very important course if you are planning to have to if you're planning to have a some further higher study in physics, then it's very essential. And uh, and also you will see slowly its applications further you go on to your like um, maybe your research and beyond. So okay, so then we can start. So yeah, hi Mehdi. So could you able to hear my voice?
Yes, yes.
Okay,
Hello.
yeah, I was just about to begin. So
Okay.
okay, so today, mostly we are going to discuss scattering theory, and so this is your final week, and for those who are also appearing for the test or exam that is going to be happening maybe in a week or maybe in a few weeks from today, so or maybe a couple of weeks, I'm not sure, but hopefully they are I would suggest them to prepare your assignments well again, and that is more or less the questions that are going to be featured during your exam. And so that is going to be the uh, like I mean the level of questions, or basically the concepts that you have gone through throughout the lecture series that you have been taught by the professor is going to be the exam. Your questions for your exam is going to be that. So all the best for that. And so moving on to scattering theory. So that is what we will look on to. So yeah, so scattering theory is a very important topic. Uh, so let me correct the date. So this is 14th. Yeah. So scattering theory is a very important topic. In physics, whether in any regime of study, whether you are talking about some research or you are talking about some important applications, everywhere it involves scattering. Whether it's something very familiar comes to our mind when we talk about scattering is Rutherford scattering, that is the scattering of alpha particles with cold atom, which really uh, gave us the mysterious framework of a atomic structure, which we are really unaware of what how uh, I mean uh, the structure of atomic the atomic structure was something not known for years, and something always physicists pondered about, and people always thought about what's the accurate description for that. So finally it came through it came through a scattering experiment. So same way, even the even people who are working on foundational theories, they also perform this scattering experiments from which they understand the strength of forces and strength of fundamental forces, and from where everything else appears. And so scattering is a very like like important topic, like it in like that like you can in every experiment, in every research, like there is some form of experiment that you need, and that is in the form of scattering. And so like in general, scattering involves bunch of particles or beam of particles or EM beam which approaches a target. So some beam of particles, some like it can be also like electromagnetic signal, so that approaches a target, so and bounces away by experiencing the potential of the target. So the target specifically means like they interact, like I mean something what happens, some a beam of particles that comes like from a large distance where there is no influence of the potential of the target, like it comes from a very large distance, and slowly when it approaches the target, it experiences the potential, and by experiencing the potential, its path deviates, its path will deviate, it will like it can reflect, it can even go through, like completely go through, like in the case of Rutherford scattering, like alpha particles, something like they, it can also like go through right through the gold foil, like which he was using. So it depends, like I mean type, what is the type of potential. So classically, when we speak, when we talk about scattering, like we throw something onto something else, and and then the thing which we like thrown towards a particular object, so uh, so like the, let's say if we throw a ball on a rock, and like it will scatter away, it will deflect from by hitting the rock. So that is like what we know scattering in classical real life, like world. So like I mean a collision between two objects or something sort of that. So but here, like how the picture is different in quantum mechanics, like something uh, we will try to see here, and perhaps like you have must have gone through the lectures which professor has like given on the scattering theory, like something which we have already known, like how scattering theory, like what is the description of scattering theory in the framework of quantum mechanics. So so briefly we'll also see that here, and some related problems, and that can also help you to solve the assignment for this week. Yeah. uh, so like in one dimension of quantum mechanics, like we know, we have we have some potential v of x, and from that potential we solve this Schrodinger equation, and from this Schrodinger equation we get solutions like this exponential of minus lambda x, minus lambda mod x. So what does this kind of solution gives, like this solution basically says that like it can at infinity, like the solution dies away, I mean the solution like do not exist anymore, or basically it gives zero value at asymptote. So that is something we know, like for a normalized wave functions or a normalized state. So these are the typical sign of a behavior of a solution at asymptote. So when mod x goes to infinity, so that is what normally you can see. So that this is something exponentially decaying nature. So these are something we know by as bound states. So and on the other hand, what you have some potentials for which you have solutions like this, which is something of a plane wave thing. So it oscillates it even at large distances. It still oscillates. It still the solution exists, and these are for example, for free potential, like I mean like for free particles, these are the solutions that you get. And in general, these are the solutions that you call them as scattering states. So that is what like we are going to look into. So like from last distances event, so you will see this solutions, they are not bound, they are unbounded states. So like they are not even normalized states. So like how normalization we see, because normalization happens when you have bound state. That means like it is bounded in a certain region of space. If you are one dimension space, then in one dimension space you will find that your wave function terminates into, or basically it is localized within a certain one dimension space. But it's not the same in scattering states. So further, what we used to do, like for in scattering states, like I mean, like we, let's say that we have some kind of arbitrary potential, uh, I mean some kind of arbitrary potential, like something random I'm drawing over here. So and let's say like some uh, for and let's say that like uh, e is greater than let's say my e is greater than 0, and let's say my e is also greater than like the peak of this v of x. So let me say this is v naught is less than v naught. So so for e greater, I mean for e greater than v naught, like I will have like quantum states which are like scattering in nature. So like I will get this kind of solutions. And if I have something e greater than 0 and also but less than v naught, then uh, I can see that like it can be trapped within this potential well. Like it can have this bound states, it can be trapped within this region. If I have something like let's say this says this is this will give you scattering states, and if I have something of this nature, I can have bound states for reason. uh, let's say this reason is something minus a to a, for reason uh, for this reason I would have bound states. So like this is roughly like what we do in one time is like the scattering states and bound states. And further like if we have scattering states like for e greater than v naught, let's say, and we see a bunch of particles coming from x minus infinity, and it is approaching towards x equals to 0, and and tries to like go beyond x equal to a, where the second peak is located, or beyond that, like then like what we see, like we basically we first like figure out the solutions in every region. So like we will find what is psi of first region, psi of second region, psi of third region, and so on. And we'll see, and after like, and we get the solution something of the form, let's say we get some solution, let's say some psi of 1, like something of reason, like ikx plus r minus ikx, and some psi 2 we get some other solution, uh, like something uh, uh, like something 2 sorry, t ikx. So so this R and D are some like the I mean the constants that we associate, and I hope you are familiar with it. Like when you solve Schrodinger equations, these are basically second order order differential equations, and from it, when you get the solution, you put some constants by hand, and then you determine through boundary conditions and so on. So what I'm saying, like if we have some kind of this kind of scattering state solutions, what we generally do, we then solve what is current associate, like as I'm like telling, like some bunch of particle is coming from x equals to minus infinity towards the potential, and wants to reach to the other end, let's say x tends to infinity. uh, by crossing the potential. So in order to do that, we need to understand what is current. So like, and this current, I think you are familiar with this very well. This is something like given as psi star del psi del x minus psi del psi star del x or dx, as I'm doing for one dimension. So yeah, and you calculate what is this j of x from here, and you you calculate this j of x in all different reason, and from here, like after getting what is j of x, you basically then define something called what is reflectance, that is something that is given as something uh, you first you define reflectance, transmittance. um, so what I mean to say, so this reflectance, that is something given as the j, uh, like uh, Z J2 upon J1, and something transmittance, something J, let's say, like if I have potential, I think you are familiar with this. If I have some potential like this, like this is something called Portwell potential, V of x, V of x. This is minus V naught. So I want to know what is the transmittance and reflectance. So what you do, you basically you define let's say I want to know what is reflectance. So for reflectance, I do like what is how much flux transmitted, and or like how much flux that is reflected upon j incident. So and then like for transmission also I do something similar, j transmission upon j incident. So this is something I'm roughly telling you. I hope you have done this all in uh, not here in this course, but previously in your all quantum mechanics course and before. So this is something like idea of scattering in one dimension uh, when you work on quantum mechanical potentials. So that is the idea of scattering. So this how much particles that were approaching towards a potential, how much got scattered, how much transmitted, how much reflected. So that is what the idea of what I mean your scattering in one dimension. But now we want to go beyond what happens in three dimensions. So in three dimension, how scattering, how do you like see the scattering, the reflectance, transmittance that we were familiar with in one dimensional quantum mechanics, how you can see that in three dimensional quantum mechanics. So to do that, let's start with a very classical notion of scattering in three dimension. So in three dimension, what happens, let's say if for example, if I have something uh, um, I mean okay, so this is a beam of particle. So this reason, this entire uh, I mean this reason is entirely something, a beam of particle approaching towards a region here. So this is something, let's say a positive charge is located here, and this is all some negative charges are approaching right here. Or let's say both are same charges, since they are uh, like uh, I mean um, yeah, so let's say both the same charges are here. Here you have some central charge here, and some beam of particles having the similar charge approaching right here, and then when they experience the potential of the charge which is located right here, then this particle which is approaching this direction, they will feel the force on or they will basically experience the potential and scatter away. So and like classically, like how we define this, I mean, like for example, Rutherford experiment itself. So like how we do that basically. Let's say, I mean, this B is basically your impact parameter, which we call. So let's say this is your zero, and I mean, from zero at a height p, you draw one circle, uh, and then at a distance of db from there you draw another circle, that like, and you, in that region, in that small elementary concentric region, you pick a very small area, that is d sigma, and that is given as b d5 db. And when they, like for example, I mean, let's say this is the charge where it is located. So and and so when this this is getting deflected like from this charge, so it will like go through a certain small volume element, like which is or basically a solid angle, which we denoted by d omega, that is given by sine theta d phi d theta. So in this case, what we do, like we define a quantity called differential cross section. So that is d sigma by d omega. So this d sigma by d omega, like it is given by, we can see d sigma is b d phi db, and d omega is sine theta d phi d theta. So from here we get this quantity, like we get this differential cross section. And to get what is cross section, so what is cross section? So cross section is the this is sigma. This is how we denote cross section. You take the complete integral of this differential cross section d sigma or d omega over complete solid angle. So what means, we found what is, I mean, we are looking what is cross section. Like let's say for this d omega, for this small d omega, like we will only get I mean, what is the contribution of cross section coming from this d omega element, that will be the contribution coming from this d sigma. But we want the complete cross section. What is the total particle scattering from this entire big circle which I have drawn here. So this is basically entire solid angle, the complete region of solid angle. This is some elementary solid angle. But for the complete solid angle, I have to integrate it by taking this small solid angle and integrating that upon with differential cross section. That will give me basically the total cross section. So like one quick example, like we can see, like for Rutherford scattering. So like for Rutherford scattering, uh, yeah, whether
Hello.
something to, yeah. uh,
So, can you, the unit of dimensional cross section or cross section is centimeter square meter square. Yes. Can you write down the unit?
uh, a unit, like it's basically like I mean, like we express in terms of like barn and something.
Okay. Okay. Bar. Okay.
uh, like if you particularly see like in high energy physics, like they would express something like maybe in units of some energy or something, because like they all work on natural units where like all the constants, they go to one, like c, h bar, and all this like physical constants, like they take it to one. So in that case, your unit can be different from the natural standard unit that you are looking for. That won't be the standard unit, like they would be using some other unit system. But like, yeah, the in general, like I have seen, like they use bar. So, yeah. Yeah, like I was speaking of this classical scattering in three dimensions. So like in um, yeah, and if you see like this d sigma by d omega, so this basically gives you the information of d sigma by d omega. It basically gives you scattered flux on incident flux. like in one dimension also, as I like trying to say like what is your transmittance. So transmittance is also something like amount of transmitted flux divided over the incident flux. So same way like what is reflectance, like that is also something defined as something like, as I was telling you, like this reflectance is generally like we say J, like let me like reflected flux over incident flux. So saying like something transmitted transmittance is something also similarly defined. Trans, transmitted flux over incident flux. So okay. So like in three dimension, like that is something equivalent of defining scattered flux or incident flux. So yeah, like as I was speaking about Rutherford scattering, so you can see that like the impact parameter in Rutherford scattering is something like given as R or multiple sine pi by 2 minus theta 2. So that is basically R cos theta over 2. So, uh, like this is something like like sorry, I mean not this like I think I wrote it for this hard sphere. Like, for Rutherford scattering, like uh, so Rutherford scattering, so like it is given as A over 2e uh, cot theta by 2. So like so remember in Rutherford scattering we have the potential as A by R. So this is like spherically symmetric potential, and so yeah. So how do you get, so like yeah, A is basically something Q1 Q2 by 4 pi epsilon naught. Uh, so uh, so like so you will see that like in Rutherford scattering like by like there would be a condition like where we like yeah, like you can check this like, I mean Rutherford scattering, like this is something the impact parameter that you will arrive with. So like and then if we have this b, so that means like we can calculate what is d sigma over d omega, which like I like tried to present here. So that is uh, b over sine theta, then you will take a derivative of b with respect to theta. So then like I can write it down as uh, okay. So like if you calculate that, you take the derivative of b with respect to theta, then further you divide b by sine theta, then that will give you a over 4 e square, then 1 over uh, sine fourth power theta by 2. So this is like uh, the differential cross section which you will get in like for Rutherford scattering, and then further like when you to get the total cross section, you do this integral d omega, then this quantity, and d omega is again like as I like told you before here, so that is sine theta d theta d phi. So like when you integrate that like with sine theta d theta d phi, then there you get the total cross section. So so that is like when Rutherford performed this like experiment and carried out what is like calculate and computed what is this cross section. So that is something using the classical notion of scattering theory. But things are a bit different when you do quantum mechanics. So, and also there will be even the results would also differ. So that is like how we can see accurately when we go to the description of quantum mechanics. So in quantum mechanics, so like in three dimension scattering, so again we start off with a Schrodinger equation in three dimension structure. So there here, what happens, like this is a Schrodinger equation, like you are performing a scattering experiment again with some potential v of r, let's say again a by r, which is the Rutherford experiment. Like so in this so in this case, like your solution will have two terms, which we are denoting as psi incident and psi scattered, where psi incident is given as uh, yeah, e to the power ikz. So how this is given is like, as I was talking over here, like if you think like if this is your uh, uh, target, where I mean where this like the beam of particles are incident on it, then from this reason, so at this reason, like it is very far away from the target. So like in this reason, like you are I mean you can like consider your wave function as something exponential ik, because it is not at this point it is not like experiencing any potential. So like so this is psi incident, that is what we are denoting right here, psi incident. And when and what happens, like let's say I mean after yeah, like this is on target, and this is and and there are some bunch of particles going this way. So at this point, we are defining psi incident as and we are defining psi incident at this point. So this is a very way apart from the target, which is over here. And further, like when after the scattering, you will see like this incident particle will just, like will scattered away all around in all possible direction. So and you will see that like when they would propagate further, like they will like they will like basically like scattered in spherical wavefronts. So like for example, for psi incident we wrote down exponential ikz, so that is plane wave. So when particles are approaching, when this bunch of particles are approaching, so their nature of wave function is something plane wave structure. But when they are scattered, you we take like they are scattered in all possible direction. So for example, like we have also here a spherical potential, which is a by r, or let's say some other potential also. So they will scattered in all possible direction, like if we are talking about three dimension. So your and we know like your quantum particles, they are all are associated with wave functions, so they behave like waves. And those waves will, when they scattered in all throughout in all possible direction, they can like go as some spherical wavefronts. So that is why we are writing the second part of the solution as something of this form, which is like for a spherical wavefront we write this kind of solution, where we have like exponential ikr over r. So that is your uh, like the that is how you write your wave. That is how you write your wave function when you have spherical wave functions. So I think you are familiar with this, maybe from your wave signal course or somewhere you have seen this. Uh, is the same?
And
Yeah. Um,
so the insidious wave function and the static wave function, it seems like the experiment of uh, interference. Yeah,
yeah, yeah,
interference.
yeah, yeah, exactly.
Yes.
Yeah, you can say that. In
Okay.
interference also, like we see that like I mean after when like it passes through like the slits, like then
Yes.
they you can say that
Spherical
like,
waveforms.
yeah, spherical wavefronts like emerges from the slit. So you can say that like, I mean, there also like something, some incident beam of photons like came, I mean, right incident on the slits, and that is what something you can say like that slit is something treated as a potential or some kind of a like a point where the your incident beams were scattered through. So, and those scattering are in the form of this wavefront, spherical wavefronts.
Okay, thank you.
Yes, you can say. So yeah, and then similarly, so as we the like as we were performing the exercise in one dimension for the scattering experiments, like we after when we have the solution, we can like like calculate what is J incident, or we can calculate what is basically current, uh, and we can also calculate what is J scattered. So this is something we will have. So this is like for J incident. I think you can very easily guess it because your nature of wave function is exponential ikz. So then uh, then your J incident has to be h bar k over m. So I hope you are familiar with this as well. Like this is something trivial, like you know it from where you can just simply calculate it. You will get it h bar k over m. And also you can see that you can also calculate this. It's not even that tough here. So this is J scattered. So or otherwise, I think like these are things like which is also like said by you. I mean, said to you by your professor. To you can find it in your lecture series. So yeah, this is what J scattered and J incident. You got the current or basically the flux you have with you, and then so we know what is d sigma by d omega as I was talking right here. So we can say like it is scattered flux over incident flux. So that is like if you divide what is J scattered over J incident. So I mean, not simply that like you have to take the for scattered flux it is something written as uh, I mean J scattered flux, it would be something R cape d, or basically d omega, I guess. uh, yeah, so this is like for incident also you will do that. Then basically you will get your differential cross section. So this is your differential cross section. Yeah. So this you get your differential cross section as f of theta square. I think this will be not d omega is solid. So basically, where the flux is given when you see through a elementary area. So the and the uh, vector of and the area vector is along the radial direction. So yeah. So this is your what this is your scattered flux. Okay. And yeah, and similarly like you like have what is your incident flux from here, and then uh, you have I mean d sigma by d omega is this thing, like scattered flux over incident flux, and from there you have f of theta squared. And initially if you see like initially I was like taking f of theta phi, but then I have changed this to f of theta because I have like phi symmetry or axial symmetry. So axial symmetry means like if you look into this diagram, so this is your phi degree of freedom. This is where how your phi varies. So along that phi, you like the cross section, the value of cross section remains same. I mean, it is symmetric. So like it is independent because you have a potential which is independent, which has spherical symmetry. So like when I'm talking about a by r potential, so that is itself some spherical symmetric potential. So you can consider it is phi independent. It definitely also has axial symmetry. So That is why we are telling for axial symmetry, you can say f of theta phi can be just f of theta. So that is why I am writing here f of theta. And when you have differential cross section, then you can have the total cross section. So total cross section, again, like going by our previous definition. So we have the integral over the complete solid in complete region. So that is how we get. So, but our next task is to understand like how we are going to find what is this f of theta. So for this, like there are various ways that has been developed, and under certain approximation we can analytically like solve them, like what is f of theta, and from there we can understand what is total cross section. So like one approach is bone approximation. So here what we do, like in this bone approximation, basically we say that like the energy of particles which are basically incidenting on the target material like has more energy than the potential. So when you compare the potential energy, you see this is the condition you will have. So under this condition, like what you can do, like you can again, like you can check back your lectures. Like this is again taught to you very well in your lecture videos. So you can see that you redefine your wave function. So this is your incident wave function as we saw earlier. So that remains as it is. But you define your scattered wave function. That is your yeah, second part of your solution of your Schrodinger equation with a green function right here. So uh, and from this green function, like you assume your like solution. This is you are assuming your solution of Schrodinger equation, which we saw right here in terms of some green function, and and when you solve that Schrodinger equation by taking this green function, you arrive with this kind of form of green function. So, but what happens at asymptote, like uh, at asymptote, that means like this is your total wave function. This is your total wave function, but when you take this wave function at large distance, that large distance by mean where r tends to infinite. So that means after when your incident beams got scattered at a very large distance, what will be the nature of this wave function? So that is given by this expression. So at large uh, distance. So the first term remains as it is, yeah, and your second term basically becomes this. So and like if you would see, like if you would, uh, if you would compare, let's say this is like this is your like equation. Let's say uh, two and 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 this is your equation one. So psi incident psi scattered is given right above it. So like when you compare equation one and two, so like you can write f of theta phi. So f of theta phi is which is there in psi scattered. So you can write f of theta phi by comparing with equation 2, which is right here. The second term right here, you can uh, write this as some integral like this. And this is what you will get the expression of f of theta phi, that is minus mu over 2 pi h bar square, and uh, d cube r, that is the volume integral that you are doing over the potential, and your q is your basically your I mean the q is basically the it is your q is basically ki minus kf. So k incident minus k scattered or k final. So the what is the initial incident momentum of your quantum particle before scattering, and k final is like what is the final uh, momentum of your quantum particle after when it's scattered. So this is the f of theta which you will get. So now, like for example, if we are given with some kind of this kind of potential, this is something we call it Yukawa potential. Like in nuclear systems, you see this. So like for this, like if we are asked to calculate what is d sigma by d omega. So what we can do? So we have the formula in our hand. So that is d sigma by d omega. That is basically we have to take the mod square of f of theta. So so that is, let's say, d sigma, yeah, f of theta, and d sigma by d omega is f of theta square. So and f of theta, like we can calculate. So uh, from here, uh, yeah, from this integral. So just a minute. Okay. So yeah. So our next task is to calculate what is f of theta, or basically f of theta phi. Like let's not let's make it general for now. Like you will see f of theta and phi. Uh, yeah, yeah. So this is f of theta. How we have defined right here. So and f of theta phi is this from this integral. So again, like so for this given potential, f of theta can be expressed in from the integral formula as minus mu z over 2 pi h bar square, and then you have the integral uh, d cube r prime, and your potential is 0 r prime over r exponential I. Q is your net momentum vector rotated with your momentum vector. So yeah, so this is your f of theta phi, which you have to calculate, and and so you have to solve this volume integral. So that is basically 2 pi h bar square uh, d r prime. So this goes from 0 to infinity, and 0 to 2 pi your d phi prime, 0 to prime d theta prime sin theta prime r prime exponential minus n 0 and q r prime cos theta. So yeah, okay. So this is what you can write. So this will be r prime. So the like you have your measure is d cube, r prime is basically written as r square sin theta d theta d phi. So from that, so that is basically r prime square. So you have already had r prime square in the numerator. So r prime from denominator like cancels out with one of the r prime in the numerator. So you are left with only single r prime. So yeah, and then like you can like you have this integral as music. So like if I think so like what I can do like so first you can do the like the angular integral first. So the angular integral basically so d5 prime integral is trivial, which is straightforward. That will just give you a factor of 2 pi. So like the 2 pi will cancel out with the factor in the denominator, and so you have mu c, and then you carry out the integral of theta prime. So so that is so that will basically give you mu z I over x bar square q. Uh, so 0 to that is dr prime cosine 0 r prime q r prime minus I q r prime. So basically you can just take what is like cos theta is some like two-way substitution, like let's call that cos theta prime is something d prime, and so that you this will become d theta prime, cosine theta will become something dt prime. So from there like you have the integral also accordingly. Like just for a moment like hello sir. Hello sir. Yes. uh, yes sir. Okay, so like that we are taking this 0 0.7 beta impact. Yes, sir. Actually, like accordingly, we have fixed our, I mean, the size of white dwarf to be at 25 RG, like initially as we were discussing. Like maybe like that 25 RG would reduce to something 20 RG, or maybe bit more lower. Okay. 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 15 like for the complete analysis, like everything. Okay. 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 Oh, 1.2. Okay. 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 Oh. Okay. 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 Oh, okay, okay. Like I have to check that. Like, so, okay, okay, okay. Uh-huh. Okay. 10 RG, right? Yes, sir. Okay. Right. Yes, sir. Uh-huh. Uh, okay. 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 Oh, yes, sir. RP by RT. Yes, sir. Yes, sir. RT by beta. So, yes. So RT is. Yes, sir. So that is R star multiplied by like M black hole by M star. Yeah. Yeah. Okay. 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 Oh, okay. 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 Yes, sir. 25 hours. Yes, sir. Huh. Okay. 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 So can I tell you maybe in after hour because I was in a TA, so like, okay, 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 sir. Like after an hour, I will do. Okay, thank you very much. Okay, okay, okay. Yes, sir. 0.7. Yes, yes. Okay, 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 sir. Thank you. Yeah, I'm sorry. So, I had to take some important call. So, yeah, I'm sorry for that. Like, might have taken a lot of time there. Yeah, but I was talking about like this. Uh, yeah, I was talking about this differential cross section for this potential. So this equivalent potential, which that is some kind of squaring potential. For that, first we have to determine what is f of theta phi. So f of theta phi, like we calculate by using this bond approximation. That is the integral expression which is given right here. And so from here, like you have this integral. So you have performed your phi and theta integral over here. Then you can carry out this integral, and you will see like basically like I'm writing. This is a bit standard integral. You will get it. So this is something given as minus 2 mu z. Like, so uh, minus energy, so that will give you h naught square n 0 square plus q square. Okay, so your q square, so here q square, let me remind you, q is basically your k incident minus k final uh, square. So basically the mod square, so that is k, that is basically your uh, k square minus 2 ki kf plus k square. Then yeah, so then it is basically your 2k square 1 minus cos theta, that is 4k square sine square theta by 2. So yeah, so that is your q square. And uh, so yeah, so you have your f of theta right now. So basically that means uh, your d sigma over d omega is f of uh, theta phi square. And you see like the f of theta that we have got right here. So q square contains 4k square sine square theta by 2, which is independent of phi, as I was talking about. Like this like the cross section values are like they are axially symmetric, so they are independent of phi, because we are considering a very spherical type potential, I mean spherically symmetric potential. So that is the consequence of that. And so yeah, and that is what I am having d sigma over d omega is 4 mu square z square over h bar fourth m naught square plus 4k square sine square theta over 2 square. So yeah, this is your differential cross section, your differential cross section for the like screening potential. When, so so I hope like it is clear to you, like, or some problem something. uh, is this clear? Okay. So if any doubt, you can like tell me like anywhere at any point, so I can try to like discuss with you. So yeah, so that was about like using brown approximation, like how you can do this cross section. So then next, like we have another way to look about what is f of theta. So as I like told you about right here, so this is a Born approximation. We only deal with cases where energy of like incident particles is much greater than the potential that we have. But in the other case, like if we in the like I mean the other way around, like we won't have be having this situation. So let's say like if we have working for low energies, so what we do, so we do another we go for another method, that is what we call partial wave expansion. So in partial wave expansion, so basically uh, like what we do, basically expand your f of theta in some form of Legendre polynomial. So again, like this is something which you can always do, you can, this is something form some form of mathematical identity that you like, for example, for any because your f of theta is some kind of trigonometric type function. So for a trigonometric type function, you can expand that in the basis of Legendre polynomial. So again, you can verify that from some mathematics text, that like for like how for a function of trigonometric can be expanded. A trigonometric function or a function involving theta, like it can be expanded like in terms of Legendre polynomial, that is PL cos theta. So your PL cos theta is basically this. So YL0, that is your spherical harmonics. So these are your spherical harmonics. Yeah. uh, and then what happens, like when you expand this f of theta, so now psi incident, you can also do this, like psi incident, which we were taking it to be some exponential ikz, or that is in terms of theta, that is basically r cos theta. So in spherical coordinates, you represent z with r cos theta. So you have exponential ikz, then that again you can expand, since your you have cos theta, like again some form of trigonometry or theta angular coordinate involving. So again you can expand in some form of Legendre polynomial, along with that is in product with this Bessel function. So again, like these are the things would be like these subtle things would have been discussed with you, like during the lectures. You can check out the videos there. So and in that case, what you can do, like if that is so, if you are expanding all your f of theta, so f of theta is your remember, f of theta is your the second part of the solution the psi scattered, which we earlier denoted with. F of theta is the coefficient of the uh, psi scattered. So like psi scattered, let me remind, this is something as we have f of theta I k r over r. So yeah, so this was the psi scattered, and we are expanding f of theta like this, and psi incident contains exponential ikz. We are expanding in this way. So in general, your total wave function can be expanded like this. So again, your RL corresponds to some form of Bessel function, and Y0 your spherical harmonics. So so yeah, so that is your what I mean Uh, so yeah, that is like in spherical wave analysis or partial wave expansion, you expand your psi r in this way. So some spherical Bessel function that is RLR and YL0 that corresponds to your Legendre polynomial. Now what happens at asymptote? So likewise, there also we saw in bond approximation at asymptote we were using an approximation. So this is an at asymptote. You were able to write this thing. The second part, asymptote means like at r tends to infinity. That means after when your incident beam of particles scattered, after long time, what happens to your total wave function? So after long time, the scattering event took place. That is, your beam of particles will reach a further distance, very large, compared to where they compared to the point of scattering. That is what we call it asymptote at r tends to infinity. So this is what the Born approximation was applied right here. So in this case, even we will see like what would be the asymptotic form here. So in this case, the asymptotic form, like psi incident r when r tends to infinity. Uh, is
Hello.
there anything? Yeah.
Yeah, so you're saying about if x
Hmm.
tends to infinity or r tends to infinity. So at the infinity, the particle will become a free particle. There will
Uh,
be no effect of the potential. So it should have a free particle function.
Not exactly. Like the because it long distance at infinity means like because like if that is free particle, I'm talking about like if you are telling like let's say let's go by what you are saying. Like if we just simply have free particle, then we cannot extract any information of what is the scattering or anything, because it's just simply a plane wave that is propagating at large distance. So we won't have that information. I mean, like what I'm saying, like it has the information within the scattered wave function or the total wave function after the event of I mean the after the event of scattering. So I'm talking about like at r tends to infinity. That is what happens like when you have I mean maybe like you can say like under some more brute approximation, you can consider this I total as something as a free particle, but exactly it won't be because like if you would see, if you understand this function, the legendary polynomial and the Bessel function involving right here. So at infinities you will have this kind of nature. So you can see that like it is almost appearing as plane wave, but with some something else, some
So
more
if
additional contribution is also there. But you are
so if
eventually getting the plane wave nature which you are telling it.
okay, so if I can relate these to the component scattering, say at first you have high frequency photon, then
uh,
when it scatters, it gives a last wavelength. So
Sorry, like what did you say?
say if I
How?
can compare
Uh,
this process with the component scattering, say at first you have a high frequency photon, then after the scattering you get a last wavelength photon.
Yeah, yeah, sure, sure. You can do that because, like, generally, this is what happens. Like, your frequency is basically that is altered after the scattering, because it won't be like when I'm telling earlier in the Born approximation also, like you have a net change in the momentum, so that all corresponds to like energy, and I mean that consequently has a change in energy, frequency, and all those things. So definitely you will see like after the scattering event there will be a change in the photons frequency. The photons are scattered through that event.
Okay.
So yeah. So yeah, I was telling like you will have a I mean you can see that like this plane wave nature is appearing right here. Like even like this is because you will see like at r I mean like when you take this to r tends to infinity limit, so you have basically this kind of nature. So this is something that will emerge out eventually, but under maybe some other brute approximation, brute force approximation, like you can eventually say that like it can become completely plane wave. But right here, when we are expanding them in the form of this partial wave expansion in terms of this Legendre polynomial and this special function, it says that still it has some different nature other than the the plane wave, because it has felt the potential, which is still has changed the as you were telling, the frequencies and all those things, all those, the features of the quantum particles. So for that reason, it would take something of different form other than the plane wave. So I hope that is something maybe you are convinced with. And yeah, and for the psi incident, like when r tends to infinity, so this is what something you're at asymptote, this is something your psi incident will look like. And then your total psi at asymptote will look like something this. So or more precisely this. So then what happens to your psi scattered? As I said, like your psi incident asymptote will behave like this, and psi and your total psi at asymptote will be this. So your psi scatter can be understood using the difference of total psi minus psi incident. So that is basically your f of theta uh, exponential ikr over r. So we are equating with that, because you're taking the difference of psi minus psi and psi incident. So that difference, from that difference you can estimate what is your f of theta. So that is what we want after all. What is f of theta? And more importantly, you will not hear. Let's see. Psi incident, as I was talking about, like it involved like this uh, sine k r minus l pi by 2 term right here. But if you see the total psi at asymptote, so it is something sine k l pi by 2 plus delta l. So you see a phase has been captured after the process of scattering. So it's just a change in the phase comes in when you are looking into this scattering process. Like initially you had some wave function that is something of this form, uh, like this is a psi incident, and that is we are writing in terms of some sine k r minus l pi by 2 over k r. And then this is like you see like sine k r minus l pi by 2 plus delta l k. So this delta l is the additional phase that is appearing right here. Or even even more precisely, you can see that as I think maybe I think you were talking about like at asymptote, like this something would behave like plane wave. Like you would see like this is more or less like this is the nature of plane wave itself, but this is something expanded in this Legendre polynomial basis. So that is not giving you exact reflection of a plane wave, which is something which we wanted to say something exponential ikz, but it is similar to that because it just expanded in some trigonometry basis, that is Legendre polynomial basis. So that is why you don't see them as a complete blend wave thing, but this is something of a blend wave nature itself. Uh, but you see that you see the plane with nature, but additionally, due to scattering, information has been captured right here. That is in terms of the phase, that is delta L k. So this delta Lk like encodes the information of the scattering event. So that is what after we want at the end. Because if you just simply say like some potential is zero at r tends to infinity, and you will again get some plane wave, which something would be something, let's say some trivial, as we started with, like exponential ikz again, then that won't have any information about the scattering. But you see like it is some plane wave nature, like with some this phase shifting. So it is again, if you plot this, you will get some kind of sinusoidal behavior. So from this, from psi minus psi incident, you can get what is f of theta, and f of theta is expressed like this. And again, if you have f of theta, then your differential cross section d sigma over d omega, that is absolute f of theta squared. And then you integrate, you get what is sigma, and your and upon integration you will find this your sigma to be this. This is your total cross section would be this thing. It, you can see it primarily depends on your phase, delta L. So delta L is the phase, that additional phase that appeared due to the scattering. So primarily your cross section depends on this phase. So it's a very key thing right here. Or even what you can see, like you can also see like this total cross section, the expression which you got right here, can also be written in terms of imaginary part of f of 0. So so this is your f of theta, and if you take f of 0, so that means theta is 0. So in that case, like and then further you take only the imaginary part, you will get this total sigma. So you can expand this basically to extract out imaginary part. You can basically extract this exponential I delta L as cos delta L plus iota sin delta L from the Euler identity. So from there, you have this sigma. And and yeah, and then like your total sigma is basically or otherwise represented as sum of all the uh, modes contributing. So L is your all the uh, mode corresponding to L. So L corresponds to different angular momentum states, uh, like for spherical S wave, P wave, you have different L values. For L equals to 0, it corresponds to S wave. So so this is sigma. So yeah, so so going with this, like we can quickly see an example right here. So using the phase shift analysis, compute the total cross section for this potential. So this is a hard speed potential, otherwise we what we know in the low energy limit. So yeah, so because as we said, like this partial wave analysis only holds valid for low energy limit, so that is why additional condition you need to accept it. Uh, so yeah, so here how you can proceed with this? Then again, you need to know what is f of theta. So let's see like what is the wave function, like. Like you can have so at low energy limit, like one more thing that is here, only s waves are going to contribute to this uh, I mean uh, for this cross section, for this potential, because again, like there is like the proof to that, like maybe you can check the lecture that is you can check your lectures on your portal, like there will be a proof on, like for the for the low energy limit, like only the lower modes, like for example x equals to 0, that is the dominating mode that contributes to the scattering. So the final cross section that you will have, that is what you get. I mean, like for example, for low energy limit, your basically what happens, like you can say, I mean, uh, uh, like for example, I mean, I wanted to say, for like when L is low, so when L is low, uh, you have, uh, I mean, so that is L basically corresponds to something, uh, something K. K is your like your, I mean, your momentum, or basically your wave number that we write. So when I multiply it with h bar, it becomes momentum. So uh, so at lower energy, so that means like your K will be less, and your correspondingly the contributing term would come from small l. So that is the other way around. You can understand, like at low energy level, only small values of l will contribute, right? So here also we consider only l equals to 0, with the only contributing term, or the contributing factor for the scattering cross section. So yeah, and now here, like if I like go with the potential which is given right here, so I can write the Schrodinger equation as uh, d square u, or dr square equals to e e yeah, for this is for the reason r greater than a, and like the centrifugal term is like that is like gone away because we are only considering, so we are considering L equals to 0 for low energy limit. So here let me write L, L plus 1, 2 r square. So this is the centrifugal term that goes to 0 because we are considering L equals to 0 limit. So L equals to 0 is the on contributing term. The S wave contribution is only that you see the dominant in this scattering cross section. So uh, for this equation, like again, you have some kind of plane wave nature. So that is something we can write it as some A cos kr plus B sin kr, or or at like the idea that we had like in asymptotic, from the asymptotic solution, like the solution are generally like plane wave nature, but with some, I mean, this phase shift which is captured due to this is important, this phase shift has to be captured because that gives you that idea that like your plane wave contains the information of the scattering event. So that means like I can write this as uh, something C sine kr plus some delta naught. Delta naught I'm writing because like I'm considering in general I could have written this delta L, but since we are sticking with L equals to 0, so this would be delta 0. So so again this is for R greater than A. So this is also R greater than A. Okay. So then what we can do, like we can use the boundary condition. So at boundary conditions is we have this hard sphere potential. So at boundary this has to be 0. So this will, from this boundary condition we can have the idea about the phase shift. Phase shift is delta 0, that is the phase shift we wanted to know in order to calculate the cross section. So we can have sine c sine kr plus delta 0 equals to 0. So from here you will find delta 0 is basically minus k ka. So at r equals to a we are evaluating. So this would be ka. So then uh, next is like we got delta zero. That means like we can now evaluate what is sigma. So we can evaluate from this formula right here. So sigma is your proton cross section. So that is for and again remember we are taking L equals to zero mode. So that is 4 pi over k square. Sine square delta zero will be the final reduced expression. So from here you put what is sine square ka, and again like as I told, like we are doing at low energy limit. So when k is less, at low energy limit, as I was telling right here, k is small. So that means you see denominator this k square is small. So I can take a limit where sigma ka tends to 0. At this case, your sigma will basically become yeah, sigma will basically become 4 pi k square ka. So just using the I mean uh, the sign, like the sin x limiting case. So from there I have sigma to be roughly equal to uh, 4 pi a square. So that is the cross section that we get for the hard sphere potential. So so I hope this is clear to you, or otherwise like any problem right here. Is this fine for you? Okay. So then another like like quick question like we can have right here, or let me say like there was something more. Okay. There is also what would be the case, like for example in the same question, like if I would have the uh, I mean let's say I mean instead of low energy limit, if I would have some other high energy limit or something, like if I let's say if this condition itself is not there here, then some other energy limit is there, which is not necessarily low energy limit, but some arbitrary energy, or let's say even there is high energy limit that we are working on. Then you will see that like in the cross section, like what is the change that you will get. Like I mean, I'm talking about the limit where uh, sigma tends to Ka is large. That means some high energy. So in that case, like what happens, your before that, let me tell you, like as I was telling you right here. So like for low energy, uh, your for low energy, K is small. So so like this implies your L is small, since your L is something up to some factors, it is uh, same with K. But for high energy, like when K is large, like you will see like the maximum L that it is possible. At that case, that like we write it as L max equals to Ka. I mean, like what I'm telling you right here, like if you want to know the contribution of other like modes, so L equals to zero is the like the dominating one right here. But for like for I mean for the higher modes, what about them? So like as we have written right here, your I mean in the scattering cross section, your L goes from like you can see your L goes from L equals to zero to infinity. So you will see that it is not exactly infinity for the like hard sphere potential that we are doing right here. So hard sphere potential, like what you technically understand, like basically even classically we see a hard sphere as something like, for example, a solid sphere is right here. Let me draw the sphere a bit more properly. So yeah, some spherical potential. So like right on this sphere, you everywhere on this sphere inside and on the surface you have the potential infinity, and so and the radius is, let's say, a. So beyond a, your potential is zero. So it is like if something like so if something is approaching some beam of particles right from here, so it cannot like go positive. But if let's say some uh, beam with some different energy, with some I mean some particle of this beam with some different energy, so it can completely pass through if it just even slides over it. So like this is a classical picture like I'm showing in classical. You can understand there is a hard sphere located somewhere and you are sending some like particles, and you will see this is what the your scattering event would look like. Everything would pass on the one which is going, like let's say the I mean the impact parameter for this case would be uh, this is B, which the impact parameter you will see that P is basically equal to A. So uh, yeah, so like here also like taking that idea, like you can see, I mean uh, your I mean you will see that uh, the maximum L value will correspond to, so L max will basically be equal to something. I mean, uh, will be something uh, AP. Let's say this is H max, so HL max. So this is like P is your like the momentum, and A is your like your impact parameter, or that is A. So that is the maximum value of it, and so that means A H bar K. So or L max is basically AK. So that is your L max. So I mean, this is what your maximum contribution can come from elements. I mean beyond that there is no more contribution, because that is what hard sphere potential is like. So up to here, like the beam coming right here. So let's say this is the last threshold particle, like which is here. So I mean, this is the last contributing uh, like mode, which would have uh, which would see like really have a very less contribution, but still the mode this is the mode that corresponds to you know I mean the corresponds to higher contribution. I mean the higher order energy contribution, but which is low. I mean the final form of the scattering cross section that you get, like the contribution which is dominated by is from the S wave, that is the L equals to zero, which corresponds to L equals to zero. So in this case, like what would be the like scenario which you will see right here. So where sigma let yeah, where k is very much greater than 1, then the contribution would go like something like we had let's say, yeah, I mean, I can now write L equals to 0 instead of infinity. I will write Ka because that is the maximum which I can have. And yeah, and then writing the full expression like 2L plus 1 sine square delta L. So that is your yeah. So this is your total cross section for the uh, higher energy contributions. And in that case, like you will have like you can further write this as uh, sigma into Ka greater than 1. Uh, so like what we will do here, so so here many L is contributing, so you will have different for corresponding to different L you will have different values of phase shift with this delta L. And for that, like since many L values are contributing, we can assume that like this sine square delta L can be replaced by its average value. So so when I replace that with its average value, so sine square delta L, like we are at K must be we are replacing with its average value. So its average is half. So so in that case, like it will be L equals to 0 Ka. So that will be 2 pi K square 12 plus 1. So so yeah. So that is like you can uh, yeah. Okay. So like I hope like the next bit is like clear to it high energy what would be the contributions. Is there any other like question in this problem? Or, is this fine for you?
Yes, yes. Okay.
Okay. So yeah, then like next I was like talking about the S-wave scattering. Like, I mean, again for S-wave scattering cross section for this potential, for this potential which is I'm having right here. Again some finite potential there. So that is what we are very much familiar in. Like in one dimension, which we often do that. So here, again, like for this final potential, you can write your Schrodinger equation, which is square root of d square 2 over dr square minus minus b is. So I am writing this Schrodinger equation for the region r less than a, and for r greater than a, like I will have this form. Uh, r. So yeah. So from here, yeah. So like from here, like you can so what you can KC minus So like I'm talking about for the reason r less than. So for r less than I can write this, and so similarly for r greater than u, I can write d square u dr square minus k square u for r greater than u. K is equals to 2 h bar square. So yeah, for r less than a, I can have the solution again, like something of plane wave as sine k0r. And from our partial wave analysis, like we know, like for r greater than a, it would be again some sine wave, like but with some phase shift delta zero. So like that is what r greater than a we saw earlier, like in the partial wave analysis, like like for I mean at r greater than a we have some sine wave, but with some phase shifting. So and and then like the for like the finite well potential, you remember, like like if you have uh, you must have done this finite well potential for at least one dimension cases, where basically we solve after we have the solutions, then we try to determine the the coefficients and all other unknown parameters which we are assigning in the solution through the boundary conditions and the properties of this wave functions of the Schrodinger equation, of the solution of the Schrodinger equation. That is basically the continuity of wave function and all this thing. So so again, like asserting to those conditions, like we can again write let's say uh, for the continue for a acceptable wave function across the boundary, it has to be continuous. So using the so at let's say r equals to a, we shall have a sine k 08 equals to c sine k a plus delta naught. Also and like this basically comes from sine uh, I mean uh, I want to say this is, I'm equating this r less than a, that is, let's say this is u1 and u2. So u1 r equals to a equals to u2 and r equals to a. So that is what you get this. And so and again, like this same you have can take u1 derivative at r equals to a, that has to be equal to the derivative of u2 at r equals to a. So that will imply you a k0 sine k0 u, that is equals to c k sine k0, sorry, k a plus delta. And now like I can let's call this equation as something one, so something two. I can uh, divide this, like again, like divide 1 over 2 This will basically give me. So this can't be a sign when like I'm taking the derivative, so it has to be cos. So like, so you take the derivative of u1, that is like that will give you k naught times a cos k naught at r equals to, that is cos k naught a. So yeah, so when you divide 1 over 2, so you basically have 10 of ka plus delta naught equals to k over k naught, that is 10 k naught a, or basically like uh, or basically what I can also write like 10 ka plus delta naught equals to ka or k naught a, 10 k naught a. So I mean, since we are doing for S wave phase shift, uh, so like for that is, I mean, uh, S wave phase shift at low energy, that is basically K tends to zero, or that means Ka over K naught A is much less than 1. So, so in that case, like what I can do, like I can just use the idea of like small values of uh, if we are taking 10x and x is very small, then roughly 10x can be equal to x. So like for small x, like 10x is roughly x. So using that, what I can write here is like ka plus ka plus delta naught is basically k k naught a 10 k a. So delta naught is to k a 10 10 k naught a over k naught a minus 1. So yeah, so that is your delta naught, the phase shift which you wanted to know, which like captures the information about the scattering event. So, and after when you have this delta zero, then it is like you can go ahead to calculate what is your cross section. So again, your cross section will be 4 pi k square. Only single mode L equals to 0 is here, so sine square delta 0. So that is again like you can write it as 4 pi k square k a, then k 0 a k 0 a minus 1. So, so there is, so this will give you 4 pi k square, 10 k naught a over k naught a minus 1 square. And like what you can see here, like this k naught, k naught a is basically k square a square plus 2 mu v naught a square or h bar square all square root. Like for small k, like this is basically k naught a is 2 mu v naught a square h bar square. So from here you can see like your this S wave cross section like is completely independent of energy. So it only depends on the potential V naught. So the sigma is roughly independent of energy. So this is this is your cross section which you um, got right here. So like, is this clear to you or any problem or anything? Any questions from here? Okay. So yeah,
It's okay.
it's okay. Okay, so uh, yeah, I mean, yeah, these are the like some different approaches. Like, I mean, some different ways to understand what is your like. I mean, f of theta basically, which we need it for computing cross section. So, like this is how like the situation changes. Uh, I mean, like you can see like initially for one-dimensional quantum systems, like the cross sections are like I mean there is no such thing as cross section, but like we uh, basically used to calculate some scattering amplitudes, that is like reflectance and transmittance, and here basically we calculate cross sections, and those cross sections are like something which like dominantly depends on this quantity f of theta as we made this analysis that I mean our wave function solution to Schrodinger equation something appears here, so which is exponential ikz, and for the incident case and for the spherical wave which is scattered one, the size scattered is exponential ikr. So and you see like a factor f of theta phi is is multiplied to it. So f of theta phi this factor basically captures here information about the potential. So f of theta phi, like more or less, like it tells that upon fixing the nature of potential, like you can have the like you can compute what is f of theta under this various approximation, and once you know f of theta, like from this f of theta only, you get cross sections. So and all this was possible like using spherical symmetries and bond approximation and everything else like the partial wave expansion. So I mean, and since also like we are also like doing with the time, I mean, like it's already like going to be the 2 hour mark. So like I think maybe we can stop here and we can have one more session. So that is going to be an additional session where we can discuss any problem like personally you are having with the course, and something more related thing that you wanted to know, like you can discuss it also, and someone I think maybe you were talking about some quantum information topic which we can discuss more, then I can
So, uh,
like
um,
try to discuss the topic about the Bell inequality and some other things which we left out. Okay, like, yeah, like, sir. Uh, okay, you are talking about like some calculator. So like that is not. I'm not really aware of it. Maybe you can write a email to the NPTEL. They can probably like reply you. Like, so like I'm not sure with like
So,
this information. Yeah, yeah.
so I'm asking for that. I want to attend the exam, but
Okay.
it will not be possible for this academic year because I mailed to them, but they didn't respond me.
Okay.
So,
Uh,
if can you please share your email number,
okay.
and
Okay.
so that I can mail you,
हाँ
and you
ठीक है.
can just give me the information in the mail. Because I am outside India, so how I
Okay,
can
okay.
attend the exam?
Okay, okay. So
So that
like,
in the next academic session, I will apply,
okay,
apply
I'm
again.
writing my email in my, I mean, in the chat box. You can note it down,
Okay.
and
Okay.
you again once again try next time. Like try to emailing them first, and if that doesn't works, then like we can like. You can mail me and I will try to reach out something some person.
Okay. Okay. So another thing is that in NPTEL there is a lot of courses on quantum mechanics, quantum enthalpy, but
Right.
I didn't see any course on relativistic quantum mechanics. So if it is possible to